Underground installations, and specifically the relationship between electrical conduits and water mains, are addressed in the National Electrical Code, particularly in Article 300.5. This article outlines the requirements for burying electrical conductors and raceways underground, ensuring safety and preventing physical damage to the electrical system. Regarding the initial question of whether a water main can be laid parallel to a conduit but above it, the answer is yes. This is permitted by the code. Specifically, Article 300.5 addresses underground service conductors and states they must be installed at least 18 inches deep or be protected against damage through other approved methods. This allowance provides flexibility in installation, acknowledging that various site conditions may necessitate alternative approaches to achieving adequate protection. As for the minimum required distance between the water main and the conduit, the NEC does not specify a particular separation distance. Instead, the critical requirement is that the water main must be protected against damage. This performance-based approach allows for engineering judgment to be applied based on site-specific conditions. Protection methods could include encasing the conduit in concrete, using a thicker walled conduit, or providing a physical barrier between the conduit and the water main. The allowance for the water main to be contained within the fill distance required by 300.5 is also permissible, provided that protection against damage is maintained. Article 300.5 outlines minimum cover requirements based on voltage levels and the type of raceway or cable being used. The fill distance refers to the amount of earth or other material required to be placed above the buried conduit or cable. However, the presence of a water main within this fill zone does not violate the code as long as adequate protection is in place. When considering underground installations and the proximity of other utilities, several other factors must be considered. These considerations ensure a safe and compliant installation that minimizes the risk of damage or interference. Firstly, the type of soil plays a significant role. Different soil types have varying degrees of corrosivity, thermal conductivity, and stability. For instance, highly corrosive soils can degrade metallic conduits over time, necessitating the use of corrosion-resistant materials or protective coatings. Similarly, soil with poor thermal conductivity can lead to overheating of underground conductors, potentially reducing their ampacity and lifespan. Secondly, the location of the installations is crucial. Areas subject to heavy traffic, such as roadways or parking lots, require greater burial depths to prevent damage from vehicular loads. The presence of rocks or other abrasive materials in the soil may also necessitate additional protection, such as encasing the conduit in concrete or using a sand bedding to cushion it. Thirdly, the presence of other utilities must be carefully considered. Coordination with other utility companies is essential to avoid conflicts and ensure safe clearances between different underground infrastructure. This coordination may involve reviewing as-built drawings, conducting site surveys, and communicating installation plans to all stakeholders. Maintaining adequate separation between electrical conduits and other utilities, such as gas lines or communication cables, is critical to prevent potential hazards. Fourthly, the potential for damage from future construction or excavation is an important factor. Underground utilities are often vulnerable to damage during excavation activities, such as digging for new building foundations, installing landscaping, or repairing other utilities. To mitigate this risk, it is essential to clearly mark the location of underground conduits and cables and to communicate their presence to contractors and excavators. Using warning tapes or tracer wires buried above the conduit can help to alert excavators to the presence of underground electrical infrastructure. In summary, while the NEC allows for water mains to be located near underground conduits, it emphasizes the importance of protecting the electrical system from damage. This requires careful consideration of site conditions, coordination with other utilities, and implementation of appropriate protection methods. By adhering to these guidelines, electrical installations can be safely and reliably integrated with other underground infrastructure. Let's delve deeper into Article 300.5 and related sections of the National Electrical Code to provide a more comprehensive understanding of underground electrical installations. Article 300.5 is the cornerstone for understanding the requirements for burying electrical conductors and raceways underground. It provides specific guidelines on minimum burial depths, types of acceptable wiring methods, and protection measures to prevent damage. Understanding these requirements is essential for ensuring the safety and reliability of underground electrical systems. The minimum burial depth specified in Article 300.5 vary depending on several factors, including the voltage level, the type of wiring method used, and the location of the installation. For example, direct buried cables typically require a greater burial depth than conduits encased in concrete. Similarly, installations in areas subject to heavy traffic may require deeper burial depths than those in residential yards. Consulting the specific tables and notes within Article 300.5 is crucial for determining the appropriate burial depth for a given situation. In addition to burial depth, Article 300.5 also addresses the types of wiring methods that are acceptable for underground installations. Generally, rigid metal conduit, intermediate metal conduit, rigid polyvinyl chloride conduit, and direct burial cables are commonly used for underground applications. Each of these wiring methods has its own advantages and disadvantages in terms of cost, durability, and ease of installation. Selecting the appropriate wiring method depends on factors such as soil conditions, environmental factors, and the specific requirements of the installation. Protection against damage is a recurring theme throughout Article 300.5. The Code recognizes that underground electrical systems are vulnerable to damage from various sources, including digging, vehicular traffic, and environmental factors. To mitigate these risks, the Code requires the use of appropriate protection measures, such as encasing conduits in concrete, using warning tapes, and providing physical barriers to prevent accidental damage. Furthermore, the Code emphasizes the importance of proper backfilling and compaction to prevent settling and shifting of the soil, which can damage underground conduits and cables. Beyond Article 300.5, other sections of the NEC provide additional guidance on underground electrical installations. For example, Article 310 addresses conductor ampacity and dirting factors, which are important considerations for ensuring that underground conductors are properly sized to carry the intended load. Article 314 covers boxes and fittings, including those used for underground splices and terminations. Article 250 addresses grounding and bonding requirements, which are essential for preventing electrical shock hazards in underground systems. In addition to the NEC, local codes and regulations may impose additional requirements for underground electrical installations. It is important to consult with local authorities and utility companies to ensure compliance with all applicable codes and regulations. This may involve obtaining permits, submitting plans for review, and coordinating with other utilities to avoid conflict. Proper planning and coordination are essential for ensuring a safe and compliant underground electrical installation. Returning to the specific scenario of a water main located near an underground conduit, it is important to consider the potential for corrosion. Water mains and other metallic underground structures can create electrolytic corrosion cells, which can accelerate the degradation of metallic conduits and cables. To mitigate this risk, it may be necessary to provide cathodic protection or to use corrosion-resistant materials for the electrical system. Cathodic protection involves applying a small electrical current to the metallic structure to counteract the corrosive effects of the surrounding environment. This can be achieved through the use of sacrificial anodes or impressed current systems. Alternatively, using non-metallic conduits such as rigid polyvinyl chloride could eliminate the risk of corrosion altogether. Another consideration is the potential for water intrusion into underground conduits and boxes. Water can damage electrical equipment and create shock hazards. To prevent water intrusion, it is important to use watertight fittings and enclosures and to properly seal all penetrations. The use of cable with a moisture-resistant jacket can also help to protect conductors from water damage. Furthermore, proper drainage should be provided to prevent water from accumulating around underground electrical installations. This may involve sloping the ground away from the conduit or providing drainage channels to divert water away from the area. In areas subject to freezing temperatures, it is important to consider the potential for frost heave. Frost heave occurs when water in the soil freezes and expands, causing the ground to lift and shift. This can damage underground conduits and cables. To mitigate the risk of frost heave, it may be necessary to bury the conduit below the frost line or to use insulation to prevent the soil from freezing. The frost line is the depth to which the ground freezes in a given area. The depth of the frost line varies depending on the climate and soil conditions. Local building codes typically specify the minimum burial depth to prevent frost heave. In addition to these technical considerations, it is also important to address safety concerns during the installation and maintenance of underground electrical systems. Working with underground electrical infrastructure can be hazardous due to the potential for electrical shock, explosions, and other accidents. To minimize these risks, it is essential to follow safe work practices, use appropriate personal protective equipment, and ensure that all workers are properly trained. Before beginning any work on underground electrical systems, it is important to verify that the power is de-energized and properly locked out and tagged out. Lockout/tag-out procedures prevent accidental re-energization of the circuit while work is being performed. Workers should also use insulated tools and equipment to protect themselves from electrical shock. Furthermore, it is important to be aware of the potential for confined space hazards when working in underground vaults or manholes. Confined spaces can contain hazardous atmospheres such as toxic gases or oxygen-deficient air. To prevent accidents, it is essential to test the atmosphere before entering a confined space and to use appropriate ventilation and respiratory protection. Finally, it is important to properly document the location of underground electrical systems. Accurate records, including as-built drawings and GPS coordinates, can help to prevent damage during future excavation activities. These records should be maintained in a central location and made accessible to contractors and utility companies. In summary, underground electrical installations require careful planning, design, and execution to ensure safety and reliability. By adhering to the requirements of the NEC local codes and industry best practices, it is possible to create underground electrical systems that are both safe and efficient. In addition to the points already discussed, let's consider some advanced topics related to underground electrical installations. These topics delve into more specialized areas and provide a deeper understanding of the complexities involved. Firstly, directional drilling, also known as horizontal directional drilling, is a trenchless method of installing underground conduits and cables. This technique is particularly useful for crossing obstacles such as roadways, rivers, and environmentally sensitive areas. Directional drilling involves using a specialized drilling rig to create a pilot bore underground, which is then enlarged to accommodate the conduit or cable. This method minimizes surface disruption and reduces the need for excavation. Secondly, ground-penetrating radar is a geophysical technique used to locate underground utilities. This technology uses radar waves to create an image of the subsurface, allowing operators to identify the location of buried pipes, cables, and conduits. Ground-penetrating radar can be a valuable tool for avoiding damage to underground utilities during excavation activities. Thirdly, cathodic protection systems are used to prevent corrosion of metallic underground structures. These systems work by applying a small electrical current to the structure, which counteracts the corrosive effects of the surrounding environment. There are two main types of cathodic protection systems: sacrificial anode systems and impressed current systems. Sacrificial anode systems use a metal that is more easily corroded than the protected structure, while impressed current systems use an external power supply to drive the protective current. Fourthly, thermal backfill materials are used to improve the heat dissipation of underground cables. These materials have a higher thermal conductivity than ordinary soil, which allows heat to be more effectively transferred away from the cable. This can increase the ampacity of the cable and reduce the risk of overheating. Fifthly, high-voltage direct current cables are used for long-distance underground power transmission. These cables operate at very high voltages, typically several hundred kilovolts, and can transmit large amounts of power over long distances with minimal losses. High-voltage direct current cables are often used for connecting renewable energy sources, such as offshore wind farms, to the grid. Sixthly, smart grid technologies are being integrated into underground electrical systems to improve their reliability and efficiency. These technologies include sensors, communications networks, and advanced control algorithms. Smart grid technologies can enable real-time monitoring of the system, automated fault detection and isolation, and optimize power flow. Seventhly, environmental considerations are becoming increasingly important in the design and installation of underground electrical systems. These considerations include minimizing the impact on soil and water resources, reducing greenhouse gas emissions, and protecting endangered species. Sustainable design practices, such as using recycled materials and minimizing waste, can help to reduce the environmental footprint of underground electrical installations. Eighthly, cybersecurity is a growing concern for underground electrical systems. These systems are vulnerable to cyber attacks that could disrupt power flow, damage equipment, or compromise sensitive data. Implementing robust cybersecurity measures, such as firewalls, intrusion detection systems, and encryption, is essential for protecting underground electrical infrastructure from cyber threats. Ninthly, workforce development is critical for ensuring the long-term success of the underground electrical industry. The industry needs skilled workers who can design, install, maintain, and operate these complex systems. Investing in training programs and apprenticeships is essential for building a qualified workforce. Tenthly, innovation is driving the development of new technologies and techniques for underground electrical installations. These innovations include new materials, new construction methods, and new approaches to system design. Continued innovation is essential for improving the performance, reliability, and sustainability of underground electrical systems. In addition to these advanced topics, it is important to stay up to date on the latest codes, standards, and regulations related to underground electrical installations. The NEC is updated every 3 years, and other standards and regulations are also subject to change. Staying informed about these changes is essential for ensuring compliance and maintaining safety. Furthermore, it is important to participate in industry events and training programs to learn about new technologies and best practices. These events provide opportunities to network with other professionals and to share knowledge and experiences. Finally, it is important to foster a culture of safety within the underground electrical industry. Safety should be the top priority in all aspects of the design, installation, maintenance, and operation of these systems. By promoting a strong safety culture, the industry can reduce the risk of accidents and injuries and ensure the well-being of its workers and the public. In summary, underground electrical installations are complex and challenging projects that require a high level of expertise and attention to detail. By staying informed, embracing innovation, and prioritizing safety, the underground electrical industry can continue to provide reliable and sustainable power to communities around the world.